Welcome to the exercises for chapter 6. Let's start with exercise 1. Here in this exercise, we will explore the relationship between the norm of a matrix and the magnitude of the values, the numerical values in that matrix. And the idea that we will explore here, which I explained in the text in this chapter, is that the norm of the matrix will scale with the range of the numerical values in the matrix. So, in particular, what you want to do here is create a 10 by 10 matrix of random numbers. These are numbers that are randomly drawn from a Gaussian distribution, and compute the Frobenius norm of that matrix. And then you repeat that 10 times for 10 different matrices. So they're always 10 by 10 matrices. You're always going to compute the Frobenius norm, but each iteration, of course, is going to be a different matrix because of random numbers. Okay, so then I average all of those Frobenius norms together. Basically, that just increases the stability of the results a bit. And then we repeat that 40 times for a range of scalar multiples of the matrix between 0 and 50. So that means 10 by 10 random numbers matrices that are multiplied by 0, and then you compute the Frobenius norm. And then the next iteration here is going to be another 10 by 10 random numbers matrices, but then you multiply them by some number between 0 and 50. It's going to be, I don't know, maybe 0.9 or something, and so on. Between 0 and 50, and then you plot the results. It might look something like this. So here we see the matrix scalar. You can see it's linearly spaced numbers between 0 and 50. And then these are the average Frobenius norms from the 10 random matrices that we computed. And what you see, not surprising when you learn about the calculations for the Frobenius norm, is that as the numerical values of the matrix increase, so does the matrix Frobenius norm. It gets a bit unstable up here because the matrices are starting to get really large. Okay, and then the other thing that we want to do with this exercise is confirm that the matrix norms are all non-negative and they equal 0 only for the zeros matrix, which happens when the scalar is 0. Okay, so now I'll switch to Python and I'll walk you through my solution. So here I have 40 linearly spaced numbers between 0 and 50. These are the scalar multiples that we will multiply by the random matrices. And here I'm specifying 10 experiments. These are soft-coded, so you can try changing these to continue exploring these concepts on your own. Okay, here I'm just initializing a matrix of matrix norms. You can see it is a two-dimensional matrix. So we have the number of scaling values and the number of experiments. So now we need a double for loop. We loop over the scaling values and we loop over the experiments. Here I compute the random numbers matrix and then multiply it by the scalar. And then I compute the norm and I'm specifying that it's the Frobenius norm. Okay, and then here I'm averaging over all of the results across the 10 experiments to generate this figure. And then finally at the bottom, I print out the matrix norms for 0. So this is the first row of this matrix here of matrix norms. And basically this corresponds to where the scaling values are 0. So obviously we are generating some random matrices, but then multiplying them by 0. And we can see that the norms of all of those matrices is 0. So the two key take-home messages from this exercise are that the matrix norm scales with the numerical values of the matrix. So the larger the values of the matrix, the bigger the norm is going to be. And that the norm of the zeros matrix is 0.